Let's look at LeetCode problem number 834, sum of distances in a tree. So this problem is rated hard, and it surely is. So what we are given here is a tree containing n nodes which are labeled from 0 to n minus 1, and we are given a matrix edges which contains n minus 1 edges and are represented by the vertices. So it is just given us to make the adjacency list. Then what we have to return here is a array of vector answer, and where answer of I is the sum of distances between ith node and the in the tree and all the other nodes. So what it basically means here is we will, for this particular example, we have 6 vertices, so they will be labeled from 0 to 6 minus 1. So we'll make an array like this, and this answer of I, for the example, this answer of 0 represents the sum of distances from each vertices to 0. So what does it mean is that for 0, if we look at all the other vertices, for 1 it is one edge away from it, so it is a equally weighted graph. So let's say unit distance 1, so it's one distance away from 0, so it will be 1. Then we see 2 is also one edge away from 0. Now 3 is two edges away from 0, so it is 2, its distance is 2 from 0. Now for 4 again 2, and for 5 also we have 2, as we have to go through these two edges, so at the distance will be 2. So our final answer will be sum of all these numbers, so 1 plus 1 plus 2 plus 2 plus 2, so that's nothing but 8. So it will contain 8. Similarly, we have to calculate this sum for each node. Okay, so let's take an example of 2. For 2, we can see that this 1 is 2 distant from 2. The distance between 2 and 0 is 1, and for 3, 4 and 5 it's 1, 1 and 1. So our answer would be 1 plus 1 plus 1 plus 1 plus 2, so that will be 6. Similarly, we will calculate it for all the vertices. For 1 it will be 1 plus the distance between 1 and 2 will remain 2, and the distance between 1 and 3 will be 3, so this will be 3. Similarly, 1 and 4 will be 3, and 1 and 5 will be 3. So our final answer for this would be for 2, not for 1. And for 1 we will have 1 plus 2 plus 3 plus 3 plus 3. That will be 12. So that is 12. And for 3, 4 and 5, the answer will be same. If only I check it, 1 is 3 distant, and 2 is 1, 0 is 2, and 4 and 5 are 2 and 1. So the answer will be 2 plus 2 plus 2 plus 3, so that will be 10, 10, 10, 10. Okay. Now I hope that you have understood this problem. So the way I was thinking of solving this problem was by BFS on each node. This is a naive approach. I know that calling BFS on each node will give us a quadratic and time complexity, which will cross the constraints of this problem, as n or is given as 10 to the power something multiplied by 10 to the power 4. So the n square will go 10 to the power 8, which will cross the time limit of 1 second. So what I think thought of doing by BFS was that if we are at 0, for suppose we are calculating the answer of I for 0, what we'll do is we'll calculate, we will call the BFS function from 0, and as we go deep, we will increase a variable in the function. Example, we first go to 1, we will increase it to 1, and we will add 1 to our answer of I. Okay, so for example, now we are calculating answer of 0, so 1 plus this is on same level, so the level would be just 1, so 1. And now we'll go to the next level from BFS, so 3, 4 and 5. 3, 4 and 5 are at 2 level, so they when we are at that node, we will add its level if it is not visited, so 2, 2 and 2, so plus 2 plus 2 plus 2, this will give us 8. And for getting answers for other node, we will just assume that our root now is the other node. For example, let's say 2, so from 2 we can say that 0, 3 and 4 are at 1 level, so they all will give 1 plus 1 plus 1 plus 1, and this 1 is at 2 distance, so its level would be added as 2. So our answer of 2 will be sum of this, which is 6, and that's what we have calculated manually. But the problem is that assuming the node every time and calling BFS function over it will give us quadratic time complexity, And so how did I then solve this problem? I spent hours on copy and pen, and then later I watched this video which really helped me with the solution. Okay, so let's see that approach. Let's try to look at this problem in terms of finding answer for the root node with the help of its children. So how can we do that is, let's take an example, the part of this example only 2, 3, 4 and 5. So for example, if you want to find out the sum of distances for the root only of this tree, that is for 2 only we have to find out. So manually you can see that will be 1 plus 1 plus 1 plus 1. So that would be 3. But if you can, we can further divide it, as it will ask its first children. What is sum of its distance? It's the root node. It has no children, so its sum of root node is 0. Okay, but this edge you see, for going to 3 we have to count it as 1. Okay, so this will return 1. Now for 4, similarly 4 is also a leaf node, so it will also return 1, as this edge is to be counted as 1. Hold on a second, if you don't understand, you will understand it when I will club this 2 in the full example. Now this 5 will also return 1. It is the leaf node and it has no childrens below it, so it has its sum of distances as 0. But for going from 2 to 5, the edge is to be counted as ones, so it will return 1. Okay, now let's take the full example. Okay, so in this example we have seen that this 0 will make calls to its children. Now this 1 here is a leaf node. Its sum of distance from its children is 0. So it will return 0 here. Sorry, it will return 1 here because of this edge to be counted once. Now for 2 we have seen that our answer comes to be 3, as this returns 1, this returns 1, this returns 1. Not when 2 will return something, 2 will not return directly this answer itself, because this edge will not be counted only once. Okay, so how many times will this edge be counted? So it will be counted once for 2, again for 3, then for 4 and then for 5. So how many times it is counted? The edge is counted the number of nodes in the subtree, that is the number of node in this subtree. So what is the number of nodes in this subtree is 4. This 2, 3, 4 and 5. So it will return the answer for this 2 that we find out and the number of children. So the number of children and itself. So 4 plus 3, it will return 7. And so our answer for the root will be 7 plus 1, that is 8. If we again look at the smaller example 2, 3, 4 and 5. So we the answer for the leaf node will be 0, as they have no children, so sum of distance for them will be 0 only, and what they will return is this answer plus their children plus 1. They have no children but they have themselves, so they will return 0 plus 1. Similarly it will return 0 plus 1, and similarly it will return 0 plus 1. So that will be 3, and that's what we have returned here. Now you must be thinking that we have found answer only for 0. By doing so, we got answer of 2 as 3. This is not the final answer, as for 2 we have considered only its children, that is its ancestors, the subtree which is rooted at 2. We have not considered this part. We have not considered this part for 2. That is the part above it. So that's why the only answer that we get from this approach is only for the root node. Whichever node we consider root with this approach will get answer only for that root only. So now you must be thinking that why this? Because this took us O of n time, and if we have to find the answer for each node, so if we do that for each node, again it will become quadratic time complexity, which will not solve this problem. So while calculating the answer for 0 in the first traversal, we use the number of nodes rooted at the children. For example, for 0, what we returned was the answer of 2, that came to be 3, plus the number of nodes at the subtree rooted at 2, that is this tree which contains 3, 4, 5 and 2, so that is 4. So plus 4, and we will return 7, and from here it returns 1, so our answers become 8. So we will need an array that will contains the number of nodes that are rooted at the number of nodes in the tree rooted at that node. So for 0, 1, 2, 3, 4 and 5, for 0 the number of nodes, that will be the total number of nodes only, because we are finding answer for 0 only. So that is 6. For 1 it would be 1, because we have to consider current node also, and then the trees at the nodes at lower level. For 2 that will be 4, for 3 that will be 1, 4, 1 and 5 also that would be 1. Okay, so now how exactly are we going to find out the answer for the next nodes, that is for 2, 3, 4 and 5? So what we are going to do is we are going to use the answer of parent for calculating the answer of child. Okay, so now we know that we have gotten answer for this 8. Okay, for this 0, this is correct. Now we have to find out answer for its children 1 and 2. So now imagine that we are calculating answer for this 2, that is child of this 0, and remember that for 0 we have the correct answer 8. So now for 2, what will happen is this edge will be considered once, this once, this for 2, and then this again for 1, and finally this. Okay, so now what we see is for 8 we had considered this edge 4 times. For 0 we have considered this particular edge 4 times. Why? Because the number of nodes here were 4, and we have to travel them, and for traveling to them each time we will have to go through this edge. But now for getting to 3, 4 and 5 we will just use these edges. We will not require to go to this edge again and again, as we are getting answer from 2. So but this 8 will contain the path or the distance for reaching these 3, 4 and 5. And if we are at 2, we don't need to use this connection here. So what we will do is from 8 we will minus the number of nodes at the subtree rooted at 2. So what we'll do is we will minus this count of 2, that is 4. 1, 2, 3 and 4. And now we have subtracted this number from there, but we need to add traversing from 2 to 1 and 0. So from traversing to 0 and 1, what we will do is we will again need to identify what are the number of nodes that are left. Okay, so here there are 2 nodes left, because this edge will be considered twice now, and this node is already handled in 8, because 8 contains this distance, as we have written 1 while calculating for 0. And what this means is that for getting the answer for 2, we just have to remove the count of 2. We have to remove the count of 2 from 8, and we have to see how many nodes are left in the tree other than the subtree. So how we'll get that? We can get by the total number of nodes, that is n, the total number of nodes minus what we'll minus? We'll minus the count of n again, because these many nodes are in the tree, these many nodes are in the subtree. So we will again minus a count of 2. So this will give answer for this 2. And if we see this for 1 also, for 1 what we will do, we will the answer for this will be 8. So from 8 we will minus the count of 1 now. So the count of 1 is 1 minus 1 plus, now how many nodes are left other than this subtree? So that will be the total number of nodes, that is 6 minus the number of nodes rooted here. So that is again 1, count of 1, that will be 1. So that will be 7 plus 5, which will give us 12, which is the correct answer. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So this is also correct. So what we will do is we will call DFS over this tree, and while doing DFS, this will give us for example, if we go make the call first here, then we will have the correct answer for this as 12. And then if we make a call here, then we will have correct answer for this also. That will be, let's calculate it. So 8 minus count of 2 is 4 plus total number of nodes is 6 minus again 4. So that is 8 minus 4 plus 2. That will give us 6. And we know the answer for 2 is 6. So we got correct answer 6. And now DFS will go to its children's and we have the correct answer for this now, and now these are the children's. So this thing will repeat again. If you want, let's do it for 3 one time. So for 3, its parent value is 6 minus count of 3, that is 1, plus total number of nodes are 6 minus the count of 3 again, that is 1. So that is 6 minus 1 plus 6 minus 1, which is 10. And we know that for 3, 4 and 10 the answer is 10 only. And that's how we have found the answer for all the trees by doing DFS twice. We did DFS twice. In the first DFS, what we did was we calculated answer for root. Let's assume we are calculating answer for 0 only in any of the we are hard coding it to 0 first for calculating the answer for assuming that the tree is rooted at 0. You can assume it to be any vertex. Okay, so what it will do is it will calculate correct answer for root. It will calculate correct answer for root. And what else it will do? It will calculate this count vector, and that's all. The first DFS will do this, and the second DFS will use this count value, and by doing DFS starting from this root node for which we have the correct answer, it will update its children and then it will go to their children's, and we have the answer for 2. So now the children's can also use this formula to get the correct answer. Okay, so now I hope that you have understood this problem. The code to this problem is attached in the description. I have explained you this through dry run, I think, sufficiently, and the DFS functions are really easy. You can directly write them yourself. Okay, so thank you. I will meet you tomorrow. Bye bye.